Okay, so this is the encryption page where you create the original encryption. The original text goes in this box. The keyword or password goes in the box that's underneath this little shape that I'm using to hide it for now. And it spits out the encryption here in hex. This column lists the original plain text character by character all the way down. This column lists the keyword or the key character by character all the way down, and it's a repeating key. It's shorter than this, otherwise it wouldn't work. And then it spits out the encryption in this third column. I have it in hex, but it could be in any format. It's a lot cleaner looking than an ASCII output. This is the formula. It uses like a custom function for XORing I found online, so you have to have macros enabled for it to work. The decryption process, you first have to figure out the key length. It's easy to do if you already know easier to do if you already know the key length. If you don't, I use this tab. So what this does, you list the encrypted message along the top here, and this is in hex form. And then I have it only going out to like 138 characters because that was enough for now, but in the program I would do the whole message. This message that I'm using is 800 characters, but this works enough for me so far. It worked for me. So then you take this and you copy it to the row below, but you shift it over one. And then you look at the first character and compare it to the one above it from the original. So that'd be the first position, compare it to the second position of the original. If it's a match, you keep track of how many matches there were. So second position against the third position against the fourth position. So for this first one, there were 3 of them that matched. Then you copy all that and paste it below again, and then compare the first position to the original. So now we're looking at the first position against the third position, the second position against the fourth position, and count how many matches you had. There were 2 in that row. You do it again, count the matches to the original, again, always against the original. There were no matches in that third iteration. There were 3 matches in that fourth iteration. There were 2 matches in the 5th iteration, and so on, all the way down. I don't know how many times you have to do it, but I just did it for the whole string. This stuff over here is I'm just using as helper columns to just help me count it with formulas. So then this column over here counts how many matches there were in each iteration. And then what you look for is the rows that had the highest number of matches. So this row, I also formatted it to be like darkest yellow will just show me where those highest numbers were. And then I also formatted it to put just an X next to the ones that were the highest, and I'm going by the 98th percentile. So whichever ones were like 98th percentile or higher in this list, I put an X by them. Adjusting this sometimes makes a difference, 96th percentile. Anyway, so then the distance between the rows that had the highest numbers in them is your key length, is your calculated key length or probable key length, because if you shift this encrypted message over by the key length, then I don't really understand why it works, but it happens that common characters match up more often if it's shifted by the key length. So this is telling me that from here to here is 9 positions, and from here to here is 9 positions. So and then from here to the next X is 36 positions, which is a multiple of 9. So it's probably 9. If I were to change this percentile to like the 80th percentile, it's no longer going to work. It's got to be the ones that are in like the highest percentile. If I were to use a password that was shorter than this, it doesn't seem to work as well unless I change my percentile. But for what I have it set up for, this works. It's calculating the key length to be 9 characters long. So the next tab is the frequency. So this automatically builds a table that's 9 rows deep. And so it takes the original encryption, and it takes the first 9 characters and puts them in this column. Then it takes the next set of 9 characters and puts them in this column, and the next set of 9 characters, and so on. So these are the chunks. So there's all these different chunks of the encryption, and the character that's in this first row is the character that's in the first position of each chunk. And then this row is the character that's in the second position of each chunk. And then it looks at all the characters in the first position, and it finds which character is repeated the most often. Because if you go to the decryption tab, this table is automatically built based on how many, based on the length of the key, the calculated length of the key. So it's 1 through 9, 1 through 9, 1 through 9. So these characters in this first position, whatever the plain text was here, was XOR'd against the same character in the key every time. So in English, the space and the E are the 2 most common characters. So they're going to be found in the plain text a lot. So every so often, when they're XOR'd against the same character in the key, they're going to come out as the same encrypted text. So if you see the same thing repeating a lot, it's probably an E or a space, because those are the most common in English. And we if we're right on our guess for how long the key length is, then that means they've been XOR'd with the same key character, the same character of the key. So based on this, in the first position of every chunk, wherever you find a 70, it should be a space or an E. So if I go to this and I say, okay, let's look at each chunk, look at the first position. Anytime I see a 70, let's put a space there and see if that gives any meaningful results. So here's a 70, I put a space, and then this output puts XORs my space against this here, which is the original, which is the encrypted text, and it puts out a P. So that's kind of a good sign because it's not a weird character, so it's possible that that's right. So I put a space because here's a 70, so I put a space. It's going to spit out a P. But a space isn't the first character of the plain text in every chunk, because if I put a space here, it's not a P, it's a weird character. But the cool thing about XOR is it's reciprocal, or it's mirrored. So if you XOR the message with the key and you get encryption, you can XOR the encryption with the key to get the message, or you can XOR the encryption with the message and get the key. So if I go by the assumption that that P is correct, if that's the first letter of the key, then that P has to be the first position of the key all throughout. But I don't know what makes a P go here. I don't know what I XOR the 39 against to get a P, but I do know if I XOR the 39 against a P, it's going to give me the plain text if that P is right. So I could put the the 39 with the P gives me the I, so I put the I here instead. Input. I could put the I here instead, and it gives me the P. So I can do substitution. If I think the P is right, I do substitution all the way throughout each chunk. Put a P here, gives me an O, so then I put an O there, puts the P where I think it's supposed to go. Do that all the way down for the first position. That's a Y, I think. Okay, and this output here is just putting out the decrypted message if the P is right. It could be an E instead of a space, but let's go on the assumption it's a P for now. And see, every time I do this and it's giving me another piece of text that's an actual letter and not a weird character, kind of just builds my confidence that I was right, that it's probably a P that goes there. There we go. Because even if you do the earlier thing where I did the space and it gave me a P, and it's like, hey, that looks good. But then if I go up and try it somewhere else, try to put the P in somewhere else, and it gives me a weird character, then all of a sudden maybe my P's not right. So I might have to try something else. All right, so let's look at the second character, the second position of each chunk. And this one only had one of them that appeared 3 times. So did this one. So those aren't really great chances, but this fourth position had a character that appeared 7 times. So that's a pretty high probability that it's one of our top English characters. So that's the 73 in the fourth position. So we go to the decryption tab and look for a 73 every time it appears in the fourth position. It's probably a space. Put a space here and it gives me an S. Okay, so let's go to the fourth position and put an S. Spits out a T, so that might be a T in my plain text to make my fourth position in the key an S. I'm trying to do this really fast. 73, put an S, make it an O. And it would take not too long, but eventually you'd start getting all the letters in here. So if I thought, oh, maybe the key is password, I could just put PASSWORD D, and it doesn't quite fit. Maybe there's a letter on the end. I mean, a number. I don't know. We'll see. So if I put the key in here, it's going to spit out the plain text. But I'm just going to put the plain text over here so the key is on the right. It doesn't matter either way. F space THOSE space. Okay, so I put the plain text that was over here into here, and it puts the password here, blah, blah, blah. It's giving me words, so I'm on the right track. I know that's the password. So if, those, etc. So then I made another tab that's almost identical to this, but instead of having to enter these in all one by one, you can just enter in the password that you think that you're guessing into this input section. So if I think it's the word password1, it'll automatically populate all these fields and then populate the output, which is a quote. So it spits out the correct message. If I were to have put a different password, like King George II, then it spits out complete gibberish. So you can see the difference between like a correct password and an incorrect password. Password 1 spits out the correct message. So then if I go back to the original encryption and remove these things, you can see that that was correct. That was the right password. So that's how it works.